To do that, we adopt a process which is known as doping. This is central to semiconductor devices. So when we start with, the IC grade silicon has a very, very high degree of purity. In fact, it has a purity of, I mentioned this in passing last time. So it has a purity of, we call this number as N9 basically. N9 indicating that it has 9 N's, 99.9999% purity. It means that it has, basically in 1 billion or 100 billion atoms, you'll find one impurity, or even more than that probably. Okay, you have to calculate that. It will definitely be 1,000, maybe up to trillion also, I guess. One part per trillion kind of a concentration, I think. You can check it out. So essentially, you have very, very highly pure, perfect lattice that you start with. Okay, but then that is not very useful because it's intrinsic. We saw that the resistivity was 100 kilo ohm centimeter. It's not enough. So what we do is we start introducing impurities. Okay, so to this silicon, we add impurities. Actually, we don't call them impurities, we call them dopants. The reason is these are what we like. Okay, so even though these are foreign atoms, we call them dopants. Okay, add dopants. When we do that, we achieve, we can control conductivity. All right. So there are various types of dopants. Now, for example, you have donors like phosphorus, arsenic, antimony. Okay. So you have a perfect crystal of, let's say, silicon like this. Okay. We saw this before. So silicon bonded to 4 different atoms. So now go and remove one silicon and replace it with a phosphorus atom. When you place a phosphorus atom, essentially we are doping with phosphorus. So what happens when you dope with phosphorus? If you look at all these dopants, right, these are called as donors, okay, or they increase electrons in the lattice, okay. So these are all what you would call as group 5 elements. Okay. Group 5 elements have 5 electrons in the outermost shell. Okay. So we removed one silicon and replaced with group 5 element, let's say phosphorus, which has 5 electrons in the outermost shell. So what do the 5 electrons do? So four of those electrons will be used up to form covalent bond with the neighboring silicon atoms. But then there is one electron which is still there extra, and this can get ionized. This electron, the 5th electron, right? 5th electron is ionized and it's free to move around in a lattice. Basically, ionized means it is going away from the dopant site. It's not staying with the dopant site. Okay, and then it can move around in the lattice. Okay, so what happens to when it moves around, electron moves around in the lattice, it can actually contribute to conduction. Okay, and if you increase the number of dopants, these are donor impurities. So if you increase, if Nd, we call them Nd, just to represent that number of donors. If Nd increases, the electron concentration increases. This is how you achieve higher electron concentration in semiconductor. So that's how we can control conductivity. Okay. What happens to the phosphorus atom? The phosphorus atom is now having charge, right? Because ionized phosphorus, right, has now positive charge. Okay. Because we have taken an electron away from the phosphorus. Initially, silicon lattice was electrically neutral, and even the phosphorus atom was electrically neutral, right? Then from the phosphorus atom, we have taken out one electron. So that's why we are creating a donor atom. Okay. Whenever you dope a semiconductor with donors, we call it N-type semiconductor. N-type means basically it has a lot of electrons. Okay, this is an N-type semiconductor. It has more electrons than holes. Okay. Now we could also substitute a silicon atom with a group 3 element. For example, here you have a list of group 3 elements, okay, which are essentially, they increase the number of holes. Okay. So what we do is we substitute with group 3. When you do that, group 3 elements have 3 electrons in the outermost shell, right? So now if you put we'll take a piece of boron and put it here in the lattice, what would happen? It has 3 electrons. So it will use those 3 electrons to form a bond with the neighboring atoms. But then it can only form 3 bonds. There is this deficiency of an electron, right? So it cannot really, boron in principle can accept one more electron to become stable or to fill its valence shell. But that electron, where will it get it from? Of course, it tries to get that electron, right? Because it wants to be stable. So where will it get it from? It will get it from one of those neighboring bonds. Okay, the neighboring bonds can break, like what is shown here, and then that will release an electron, and that electron will be captured by the boron atom. Okay, so boron atom captures electron from lattice. Okay, and this process is called ionization. Basically, it becomes to become ionized acceptor. We call this as Na. And actually, this acceptor has a negative charge now, because initially the boron atom was electrically neutral, but now it has accepted an electron, so it becomes negative. So Na minus we denote. Okay, and similarly in the case of Nd, we call it Nd plus, because the donors acquire a positive charge. So Nd plus is basically, and then here it is Na minus. So acceptors acquire a negative charge. And of course, we have a hole which is now in the lattice. So if you increase the number of Na increases, holes increase in the lattice. This is how you can create a p-type semiconductor. A semiconductor which has more holes is known as a p-type semiconductor. Which has more electrons is called an n-type semiconductor. All right. So these electrons and holes can contribute to current conduction. Now let me ask you a question. Will the ionized acceptors or donors contribute to conduction? Please think about it. If you want, you can pause the video and then think about it. So, will ionized donors or acceptors contribute to current conduction? Will they? Well, they cannot. Okay. This answer is going to be no. The reason is they are fixed in lattice. These ionized impurities or dopants are actually bonded to 3 different or 4 different silicon atoms next to them, right? So they cannot move, and so they cannot contribute. They're only contributing some charge, and this charge is actually fixed charge. Remember, these ionized donors have plus charge, acceptors have negative charge, and these are actually fixed in the lattice. They cannot move. What can move is the electrons and the holes they actually add into the lattice. All right. So this is an important process, and this is very, very important that you get a hang of it. So the most common dopants are listed here. For N-type, we have phosphorus, arsenic, and antimony, out of which usually phosphorus is what we use most of the time. Sometimes we use arsenic. Antimony, I have not seen that many examples. Similarly, for P-type, I find that most of the time it is boron. Even gallium is actually very rare. Okay, so this is how you dope semiconductors. So same dopants would work even for germanium. But what will work for gallium arsenide? Gallium arsenide is a 3-5 semiconductor. What do you use? Shall we use group 2 and group 6? Yeah, we can use them for gallium arsenide. it turns out that you could also use group 4 elements. For example, you can use silicon as a dopant in gallium arsenide, because silicon can either take away electron or give an electron, depending on whether it is, taking an electron, I mean, to which it's replacing. If you replace gallium, you get one type of a doping configuration. If you replace arsenic, you get other type of doping concentration. Okay, so think about it. So sometimes a dopant can actually act as both donor and acceptor. Those are called as amphoteric doping. Okay, basically it can be both electrons and holes. Amphoteric dopants. Silicon in gallium arsenide is an example of that. Okay. So well, anyway, we are not talking about gallium arsenide. So silicon, this is enough. Okay. All right. So what? This is basically physically we understand what's happening. We're replacing an atom and then it is causing these things, right? But what is happening with the energy bands? Okay. So I said that the dopant, the donor is getting ionized, so the acceptor is getting ionized. But then that requires some energy. How does it get ionized? Okay. So it also turns out that these energy levels, right? Because we have studied these energy levels that come because of the atoms and lattice and all that. We understand that from the particle in the box, right? So these dopants are actually quite close to the silicon atom, right? In the periodic table, it's just next to it in the periodic table. So when that happens, it turns out that the donor energy levels, this is the donor energy level, ED, okay, I call it. You have the original EC and EV, and you can also put a donor level, which is ED, okay? So donor energy level is close to conduction band. Okay. I mean, why this happens is not necessary, but you can think of it like, it's quite close in lattice constant. I mean, it's just next to it in the periodic table, so you could expect that the energy levels are also similar. Okay. So okay, you have these donors, and if you are at 0 Kelvin, okay, 0 degrees, what happens? Your valence band is completely filled up with all the silicon electrons, and then there is this donor level, and that has some electrons, but those are all in the donor itself. They are not free to move around. Okay, so basically, that's why we show the electrons as at the donor level. That means they are tied to the donor atoms. So they are not going to contribute to conduction. Okay. When will they start contributing to conduction? They should get ionized. That means electrons should get out of the donor atom. And to do that, we require some ionization energy. And this turns out to be about 45 milli-electron volts, okay, for phosphorus. Okay, for phosphorus. Okay, so this is quite small energy. We said room temperature energy KT, right, was 26 milli-electron volts. So quite close to that. So as you start increasing the temperature, okay, we are adding energy to the lattice, right? So then slowly you find that these electrons are actually moving into the conduction band. Some of these electrons are moving into the conduction band, okay, and they are getting ionized. All right. And of course, as further temperature increases, you'll have, if you reach room temperature is 300 degrees Kelvin, okay? And at that temperature, it is sufficient, and you'll see that all the donor atoms are ionized. That's why here at room temperature, donor level is empty. That means all the donors have been ionized, and you have Nd plus. Okay, so let me just repeat it one more time. This is an important process. Okay, so at 0 degrees, what happens? All donor electrons. Let's only talk about donor electrons. Okay. Donor electrons are bonded to donors, right? So basically, there are no electrons available for conduction. Okay. Now, as you increase temperature, donor ionization starts. That means electrons start escaping from the donor atoms. Okay, and this implies that you have electrons in conduction band. That means they can carry current. Okay. You might ask, as temperature increases, you should also have electron hole pair generation. You will have some electron hole pair generation, but remember, the energy required for electron hole pair generation is Eg, whereas the energy required for donor ionization is very small. It's about 45 milli electron volts. Eg is 1.12 eV, right? So basically, the donor ionization threshold is much smaller than EHP threshold, I will say. By which I just mean that you need energy, higher amount of energy to create electron hole pair. So what you see is that most of the electrons are coming from the donor level instead of from the valence band. But as you further increase, yeah, of course, at room temperature, we will actually have to calculate how many electrons are there and holes are there. We'll calculate that. But at room temperature, all the donor atoms are ionized. Okay, and actually even some electrons from VB move into CB, right? Basically EHP generation happens. Okay, so this leaves some holes as well. Okay, when the donors are ionized, you have electrons and implies few holes in few holes in valence band. Okay, so there is, that's why I indicated a small, one hole here, essentially just to indicate qualitatively what happens. Okay. We will actually compute this, down the line, how many electrons can be there, how many holes can be there. Okay. So whenever, by the way, whenever you introduce a dopant, right? Let's say if you're introducing donors, you're essentially creating electrons, lot of electrons. So electrons are called as a majority carriers. Okay, but in the process, you'll get a few of the holes. In this case, holes are called the minority carriers. Okay, you'll see that the situation is reversed when you have acceptor, dopants. Okay, the same story. Basically, in this case, acceptor level is close to EV, valence band. Okay, and it has a small ionization energy. Ionization energy for boron in silicon is also about 45 MeV. The numbers are, we can check up from the textbook, but I think it should be about 40 to 45 MeV or something. Okay, so when you have this, what happens to as the temperature changes? Well, at T equal to 0, all acceptor states are empty. Implies no current conduction, right? When there are no states available, how can everything is bonded, right? Every electron is bonded, so there is nothing, there is no conduction. But as T increases, you start seeing that some of these electrons from the valence band jump into the acceptor states. When they jump, essentially the boron atom is capturing the electrons from the lattice. And so, basically, we are saying that acceptors start ionizing. Okay, by capturing electrons from valence band. Remember, valence band has lots of electrons. Okay, the same story again. Even the ionization threshold here is actually much smaller than the electron hole pair generation threshold. The same story. Okay, and as you further increase temperature, you see that all acceptors are ionized. Okay, so let me do one thing. Let me say ND, right? Basically donor atoms. When you add donor atoms, you create electrons. Okay, Electrons are added. Electrons are added in significant number actually. So basically, electrons are majority carriers, and holes are few in number. So we call them minority carriers. Okay. Whenever you dope with donors, you get electrons as the majority carriers and holes as the minority carriers. And when you dope with acceptors, Na, okay. So basically you are adding more holes because you can control the number of acceptor ions in the lattice. Okay. So if you add more holes, you get holes as the majority carriers, and electrons, sorry, electrons, I should say N, right? N is the minority carrier. All right. So this is this is first time I guess we are introducing this. So this is, you should think about it. Just the definition, we keep talking about it multiple times: majority carriers, minority carriers. Whenever donors are added, electrons are majority carriers and holes become minority carriers. Whenever acceptors are added, holes are the majority carriers, electrons are the minority carriers. We will see why they are also, because we will compute the numbers and you will see the difference in the ratio. Okay. All right. So, I mean, this temperature dependence is a very, very important part of understanding what is happening in the lattice. So I just plotted a different graph. Okay. So let's imagine. Okay. Now, so far we have not taken any numbers. Now let us try to imagine. We have added ND. Okay. ND equal to 5 into 10 power 14 per cm cube. This is the number of dopants I'm adding into the lattice. How I'm adding, we can think about it later. But I'm adding donor atoms of 10 power 14, sorry, 5 into 10 power 14. So what happens as you increase the temperature? This is very, very good way of understanding. If you understand this particular graph on the right, you would have understood a lot about semiconductors, okay? How they are operating. So when temperature is 0, I mean, this is not a log plot, okay? This is not 1/T plot. This is simply the carrier concentration N and versus temperature. Okay? So as the temperature is very, very small, I mean, let's say assume 0 temperature. What happens? You know, N equal to 0, right? N equal to 0. The reason is all the donors are not ionized and electrons are all in the valence band. There are no electrons, no N in Cb. So there's no carrier concentration at all. N is 0. But as you increase the temperature, you'll start seeing that you have donor ionization is happening. And this particular part, right, whatever we called as partial ionization, as the temperature increases, slowly the electrons concentration increases. Okay? This is basically partial ionization, what we talked about in the last couple of slides. Okay? At some point, all the donors are ionized, right? And you don't require a lot of temperature to achieve this. Okay? So when you have all the, this is a point where all donors are ionized. Okay? And then there is nothing much. If you increase the temperature further, what should happen? Well, as you increase the temperature, there will be electrons in this part, right? Electron hole pairs can be created. Right? Electron hole pairs generated because by electrons moving into Cb, right? They jump from conduction valence band into the conduction band. That can happen. So because of that, you have EHP generated. But that number is very, very small. Remember, at low temperatures, the electron hole pair generation process is very, the number carriers generated is very small. So if you have a semiconductor which is doped, okay, doped semiconductor, I'll call this as extrinsic semiconductor. Okay, undoped semiconductor. I'll call this as intrinsic semiconductor. Okay, this is the language we use. So if you have an extrinsic semiconductor, once you have ionized all the donors, the carrier concentration cannot increase. Okay, so it sort of stays constant because there are no further donors to be ionized, all of them are ionized. But then as you continue increasing the temperature, at some point the Ni will start increasing, right? We saw that even if you have an intrinsic semiconductor, as you increase the temperature, more and more electron hole pairs are produced. So at some point, the electron hole pairs produced from the intrinsic contribution or from the valence band, electrons jumping into the conduction band increases. At some point that will take over, because of which your carrier concentration now in the blue, it starts increasing. Okay. So in this case, when you reach this regime, we call it the intrinsic regime. Intrinsic regime. The reason it is intrinsic regime is that the increase in the carrier concentration is dominated by the excitation of electrons from the valence band into the conduction band. Okay, so this is the intrinsic regime. And at intermediate temperatures, this is the extrinsic regime. Because essentially the carrier concentration is flat because all the donors are ionized. Okay, there's nothing more to ionize, so the carrier concentration doesn't change with temperature. And in the very small temperatures, up to about 50 Kelvin, this is usually up to about 50 Kelvin, 0 to 50 Kelvin, I would say, or even 100, maybe a little bit, okay, close to that, 50 to 75 Kelvin. At that temperature, you will see that only a few of the dopants are ionized, and because of it, you have an increase in the carrier concentration. So you should be able to plot the carrier concentration changes as a function of temperature. Okay? So the blue one is extrinsic semiconductor, and the dashed line, this is an intrinsic semiconductor. Sorry. This is an intrinsic semiconductor, wherein you have, as you increase temperature, we already saw that Ni keeps increasing. N equal to P equal to Ni, that increases. Okay. So, well, yeah, I would like to stop here. It's already 55 minutes. So I would like to stop here. So today what we did was, we started out with basically how we introduced a concept called as effective mass in semiconductor. We said, how the carriers move about in a lattice can be captured by this quantity known as effective mass, and that can be calculated based on the EK dispersion. We gave you a formula to calculate the effective mass. It's simply the second derivative. It is proportional to the second derivative. And we gave you, we showed you one problem. We didn't solve it, but I'll leave it as an assignment in the homework. Okay? You just solve it a few cases, and that will help you. But the concept should be clear. If you are not, just revisit this slide. Okay. And then we talked about intrinsic carrier density, how that changes, how it varies across different materials, germanium, silicon, and gallium arsenide, and then how it changes with temperature. So this is what, again, we came back in the last also. So finally, we talked about doping. Doping is essential to semiconductors. Okay. So please make sure that you understand doping. We keep using this again and again, so you should be quite comfortable with this. All right. So we explained how donors will impact, how the ionization happens in donors and how it happens in acceptors. Okay. So whenever you dope it with acceptors, we get holes. So we got it P-type. We call it P-type semiconductor. Whenever you dope it with donors, we get electrons. So we call it N-type semiconductor. So please try to summarize it on your own. Take a piece of paper, write it on your own. Make sure that that is correct. That will help you clear up any concepts. Okay. So conceptually, the physics has been described quite, I think, quite well. So you just have to make sure that you follow through the chain of thoughts. And once you're able to do it on your own, you should be good for the next lectures. So in the next lecture, what I'll try to do is, we'll introduce a few more things. We'll actually go deeper. We will talk about what is known as Fermi function, how that influences carrier density. And we'll also start, calculating some numbers. Okay? All right. I'll meet you in the next lecture. Till then, take care. Bye.